Let us talk about the relational database scaling. So when you initially launch your MVP, you just wanted to launch for your first 100 or first 1,000 users. But as and when your app goes viral, your number of users increases, which basically means that the traffic on your application increases and the traffic on your database also increases. So basically, you have to eventually scale up your database server as well. But scaling database server is not easy as you scale your application server, because here, in application you can just add more instances and you can horizontally scale it. The reason is because there is no state maintained in the application server in most of the cases, which is not the case for database server. In database, the data is the state which is maintained. So eventually, if you want to add new instances or you want to scale it, it is more complicated as compared to application server scaling. So let us understand the step-by-step guide how you should actually scale your database. This question is also a lot of time asked in interviews as well, and people just directly jump into sharding, partitioning, and um, very complex use cases, which should not be. You should directly not jump into sharding partitioning. There is a step-by-step guide you should follow when you are scaling up your relational database. So step zero is the very foundational tuning and optimization. What this means is, let's say you identify that your database has slow queries, or it has connection timeouts, or it has high CPU utilization or DB servers. Before actually touching your infrastructure, which means adding more instances of database, what you should do is you should actually optimize your queries, schemas, and connection. When I say optimize queries, which basically mean you have to ensure that there is no full table scan happening on your database tables. So what you have to do is you have to look into your read queries. What are the select queries happening? What are the joins happening based on your query patterns which is coming to a database, and then find out if it is going to the right indexes. So what you do is you find out the slow query, you explain, analyze it, which will basically give you a query plan for your query, right? So based on the query plan, what we will see is like how the data is being accessed from the database. If it is a full table scan, basically this is something you have to avoid. So what you have to do is you have to add indexes properly on the table. Other thing you will see is a lot of connection timeouts, because your database queries are slow, so the other connections are waiting and eventually they will time out. So what you have to do is connection pooling is also one concept you could readily have it in your application server. So what connection pooling is, when the application app server talks to the database, it does a bunch of steps. It creates a connection, which is a heavyweight object, and then it does a handshake with the database, tries to do authentication, all those things it do. So that is a bit time-taking process, as well as take up a lot of resources from app and database side both. So what you could do is eventually create a pool of those connections readily available, and when the select query is coming or write query is coming, the application just take that connection from that connection pool and use it for read and write. Other thing is, when you identify that there are some joins which are happening, and the data is also very static, it's not changing much. So what you could do is like you could denormalize the data also, and instead of having it in multiple tables, you could have it in one table. Obviously, the trade-off is some redundant data, but which is fine, right? The data is redundant, but eventually that's the trade-off you're taking. So you're avoiding joins by denormalizing the data into a single table. This is against the concept of normalization, but sometimes you have to do it based on your needs. So you have to do this continuously every time. If you identify slow queries, identify bottleneck, add indexes, remove indexes, add connection pooling, add denormalization, all those things. If this is not enough, right, you have done all these things, you come to the step one, right? Um, you have added proper indexes, you have done denormalization, you have added connection pool. Still, the CPU utilization of your database service is very high, right? So you end up having no option other than vertically scaling up, which means you are increasing the CPU power or the RAM and storage of your database server. So with most of the cloud providers, this is like coming with a zero time term. So you don't have to worry too much about it. And at the application side also there is no changes. So all you have to incur is more cost because you're moving from smaller instance to a larger instance. For example, if you take the AWS Aurora configurations, right? If you want vertically scale from medium to large, you basically move the database instance from R5 to R7, right? And most of the cloud providers comes with a zero downtime when you do the vertical scaling. So this is one of the easiest way when you hit your scaling limits on your relational database. After you vertically scale also, still you see that the read queries, there are a lot of read traffic actually, and the read queries are not scaling up. So another thing you could do is, which is step two, is adding read replicas. So you identify that after vertical scaling you have a lot of read traffic, and the single database server is not able to handle it. So what you do is you create a master slave setup where all your write will go to master and the reads will go to the from the replicas. And for a single master, you will configure that there will be 3 to 4 read replicas. So what eventually happen is your reads will be distributed to multiple different DB instances, which are synchronizing the data from the master. So this is one of the setup usually we do. Uh, so when you have to do it, the primary instance CPU is high due to read queries. What actually you have to do it? You have to create a read-only copies of your database, right? And how actually you do it? You add read replicas, right? You have to do certain application level changes, right? So these are application level changes. You have to identify if this is a read query. So in that case, you have to add logic in your application that if it is a read query, it has to go to the read replica, right? Now, there will be obviously a load balancer in between because there are multiple read replicas. So load balancer will take care, it will direct your query to one of the read replicas, and data is getting synchronized from the master. All the writes will go to master and they will synchronize the data to the read replicas. This might have some eventual consistency because your data is syncing with some replication lag, but you could also achieve strong consistency when you're writing it. So it again, it's very configurable. But in most of the scenarios, it becomes a little bit eventual consistent. But the order is very low in the order of milliseconds. So most of the time, this is fine, and this is very well done in a lot of the. If you read about a lot of the different architecture for read scaling, this is one of the very best technique which is used in the industry. Okay, so you have now done vertical scaling. You have also done the read scaling. You have added replicas. Still, your some of your read queries are very heavy and choking up the database, right? So when you identify such queries which require a lot of joins and which are querying a lot of different tables in a single query, and which needs a lot of data. Maybe like let's say you want to have all the orders of the India region for the last 6 months, right? So these are more of analytical queries, right? In this, first of all, you should not direct analytical queries your transactional database. But even if you're doing it, there are some sort of techniques you could have, like materialized views, where you create a view and the result will be pre-computed on that view. So what you do is you identify the complex query, slow query, which is aggregation of multiple joins, and you create a materialized view of it. When you should use it for dashboard analytics and reporting, where near real-time data is also fine. Like you don't need always real-time data. Obviously, the con is it is not real-time. So your database will refresh your views periodically based on the data which you have defined your view. And if your complex query will directly query this view instead of querying the data real time, it will query the pre-computed data which is already present in the view, and in the background it is getting refreshed. Okay, after you've done all this, the step 4 is the next step. After you've done the materialized views is your application level partitioning. So assume that there is a very massive table in your database, which is having billions of rows, right? And every time you query it has to scan a lot of data because the data size of the table is very high. So what you do is like you split the last table into smaller physical pieces because this will help your database to only scan a subset of data. We'll understand it how, right? Let's say you have an invoice table which have a lot of rows, right? So what you do is you partition that table into multiple partitions. These are still the table, but these would be individual table, which is the parent table would be invoice table, right? So how you create the partition? You just create table and you partition it by some field. So mostly the partition is done either by hash partitioning or range partitioning. Here we are doing a range partitioning, and the partition keys is invoice date. So basically your data is getting partitioned based on the date, right? So this is first step, you create the table, right? And then you create the partitions. For example, in this example, I have created two partitions. So all the data which is in year 2023 will go to invoices 2023, and all the data which is created in 2024 will go into the invoices 2024 partition. So the good thing is your application doesn't have to remember which partition the data it has to send, right? It just write the data into invoices table, and internally it will see that already there are partitions created on this table, and the partition key is invoice date. So it will find which partition it will fall into, right? So based on that, it will automatically choose the partition and it will write the data inside that partition. The real magic happens when you query the data, right? So for example, I query select star from invoices where invoice date is some date from 2024. Now the database knows already all the data which is of year 2024 relies in this partition. So instead of scanning the complete table, it will just scan the relevant partition. So this technique is called partition pruning. So this is a very effective technique if your certain table on your database grows very, very big, and then you have read queries, a lot of read queries on your database, which are specific to some users or specific to some date range. So basically in that case, you do table level partition. Again, all these things we have to do at database side. Applications for application, there'll be still a single table. So all the read writes will be going to the invoices. Internally, the database is smart enough that it will identify based on your partition key which partition it has to write and which from which partition it has to read. So this is one good part of doing application level partitioning, that the application side you don't have to do any changes. And also remember, all these partitions still are in the same DB instance. So these are on the same DB, same physical DB server. It's just that logically we have divided a big table into multiple small tables so that the database only read the relevant data when there is a read query. After this, after you have done all this index optimization, read replicas, your vertical scaling, table partitioning, then only you should think about doing sharding, because sharding has a lot of cons. It has really a lot of cons, because I'll go to the cons first, because a lot of people don't understand what are the challenges with sharding, and they eventually just jump into the sharding. It comes with a massive application level complexity, because now your application need to know which database, physical database instance it has to hit, because now you don't have a single database, right? So your application has to talk to multiple database. So it comes with a massive application level complexity. Cross shard asset property is no more possible. So because now you have multiple database instances, your cross shard query doesn't give you asset compliant, because now they are not a single database server. They are multiple DB server. They can independently give you asset compliant, but if your query is doing cross shard scanning, then you cannot guarantee that asset compliance. So first, let's try to understand what sharding is. So what you do is when you have to do is right when a single writer instance is not able to handle all the write load. So now your single writer instance is not able to handle all the write loads. Eventually, you have to have multiple database instance which can take up the write. So we had a read scaling, right? If you see read scaling, what we did, we just had a single master and we had a lot of read replicas. But in this case, our single master was able to handle all the write queries. But now we have come to a situation where we have a lot of write traffic as well. In that case, you have to have multiple database servers for write as well. So what you do is you distribute the write load across multiple database servers. You create some shard key. Your shard key would be either based on, let's say in this example, I've taken region. Region is a shard key. And if the user is of US region, all the data will go to DB1. If user is from the EU region, all the relevant data will go to EU DB2. If it is from the APAC region, it will go to the DB3. So all this complexity will come into the application. It now has to have a logic to first identify which physical database server it has to talk to, right? So that's one level complexity which it comes with. But there are a lot of advantages as well. Obviously, there is always a near infinite horizontal scaling. You can add as much write database instances, but eventually you also deal with the rebalancing and all those stuff. It greatly increasing the read write throughput because now you know you have to only talk to a specific database instance based on which region it is. It has higher availability because let's say if this database goes down, so all your app will not go down, it will only go down for the US region, right? It will still work for the EU region and APAC region. So it gives higher availability and fault tolerance. Cons are, as we discussed, now if there is a query which is going to both the shards, right? It is not as it compliant. It is not as it compliant because these are two different physical database servers. The queries from cross shard will also be inefficient. And if you want to join data between those, that's also not possible. So it comes with a lot of cons. That's why sharding is really a complex thing to do, and you should only do it if you have exhausted all other things before sharding. So as I said, sharding should only be applied if you have exhausted all other database choices. Let's also talk about some other DB scaling techniques, which is not directly like you are scaling your database, but some other techniques which could avoid a lot of traffic on the database. One is application level caching. So what you do is you cache the static data into cache, maybe some Redis or Memcache. So what you do is when you are reading something, you first try to read it from cache. If it is not present, then only you are hitting the database server. In these cases, you eventually reduce the traffic on the database. You're not scaling the database. Eventually, you're reducing the traffic on this database. So in some sense, you can say that it's way of scaling your database. So the obvious pros are you reduce the read latency, right? And you reduce the load on the primary DB because now some of your data is already served from the cache. It is also increases system availability in some cases for some seconds, right? If this is down database, you can still serve your app through the cache. There are a lot of drawbacks also as you increased other DB scaling techniques you can introduce is you can introduce the application level caching, which is cache the static hot data in the cache to avoid query the DB. So once you identify that there is a set of data which is very static, which doesn't change too much, and it's been queried a lot. So what you can do is you can put that data into a cache, application level cache. So this cache is a distributed cache, which is accessible from all your application servers, different application servers. Um, so what this will do is indirectly it is reducing a load on your traffic on your DB. So one of the thing you have to consider is you only can cache data which is not changing too much, because then you have to invalidate the cache and update the cache as well. So the pros of this approach is it reduces the read latency because you are querying the data from cache. You are not doing a database query. You reduce the load on the primary DB, obviously, and you also increase system availability in some sense, because for some time, if this DB is down, you can still um, query the data from cache and serve your queries. There are a lot of trade-offs as well. The scale data problem, as I said, if the data is changing too frequently in the database, then you always have to update the cache. And in some cases, if you're not able to update the cache properly, you end up serving the wrong data. Cache invalidation is very problematic because you always have to sync now database and cache if there is a lot of writes happening. It is not a solution for write heavy workloads because, as I said, it is very difficult to sync two data sources um, with the data. Other approaches, you could introduce queue to your write load smoothing. So what this means is if there is a lot of writes happening to your database, right, and you're okay to have a little bit eventual consistency in the sense that if your data is written up with a bit of delay, then what you could do is you could introduce a queue in between your database. So what this will do is it will handle those spikes on the write access pattern. So if there's a lot of write happening in the very short amount of time, if there is no queue in between, the database might go down if your application is directly writing to a database. But if there is a queue in between, it will buffer those data and it will write based on how you have scaled up your consumer. So you can scale your consumer based on your DB performance limits. Uh, so even though there are a lot of writes coming, your DB will not always be writing those data as soon as those are coming. So it will be buffering. It is good for scenarios where you are okay to have eventual consistency, because once you have introduced the queue, some of the writes might not go through at the same time. It might take some time. So if you are just reading the data, it might not be very consistent. It might not be fresh. It might be some staleness in the data. There is other challenge with this approach is if the data which consumer is consuming and inserting into DB, if those get failed, that is a little bit complex to handle, because from your user side you've already said the data has been written as long as you've write it in queue. You don't know what's happening after that. But if during the consumer side, if while processing the data is not correctly written to the DB, then it's a problem because you've already let know that for user your data has already been written, but actually it's not been written to the database. So in those scenarios it becomes a little bit complex to basically handle those scenarios. The pros are definitely there. It enables asynchronous processing into your system. You have more increased system resilience, because if for some time your database is down, your messages are still there in the queue. So you're not losing those data. You're still that data is there in the queue, and once the database comes up, your consumer can process and insert your data into the database, and it can handle the spikes, as I said, because you're buffering the data into the queue.